All right. Good morning. I guess
Good
let's wait.
morning.
Yep. Good morning, Dawn. Let's wait a little bit to see if some other folks will join us. I see somehow my screen is quite black. It's weird. Let me try again. Ah, okay, that works. Oh, you guys don't do you guys see like my screen or you see a black screen?
It's still black.
It's so weird. What's going on here?
Yeah, it's black right now.
Like we see your cursor, but just not like the content you're screen sharing.
No, I know. It's not supposed to be this way at all. You don't see anything, right?
Yeah, it's just completely black.
Wow, this is new. I hope Zoom did not destroy my my way of lecturing. Um, let me sign out and sign in again, okay, guys? Let me try to see if that works.
Oh, we can see it now.
Yeah, I can see it too.
Yeah, I know. Thank God. I mean, like, this is the only way I know how to lecture. If it doesn't work, then that's pretty troublesome. All right. Cool. I think some of us are here. All right, so good morning. We'll continue with our lecture today. Keeping in mind that the second midterm is next week. So the material will be capped by today's lecture. I'll let you know more precisely what that would be. But I think most likely it will be capped with, all the exotic options. So I'll confirm that, all right, after we're done with the lecture today. But so midterm 2, so next Wednesday, right? The material will be, I think, jump processes, everything but, and exotic options, everything about it. So roughly speaking, in terms of the notes, it corresponds to, let me see here, chapter 1, 2, 3, 4, 5, 6, 7. But like I said, the notes is larger than life. Okay, there are a lot of details in there that I did not cover. So in the lecture, so if I did not mention certain details in the lecture, I won't ask about it on the exam. Okay, so the notes are there for your reference, and I just mentioned this as a like a easy anchor for you to kind of have an idea of what kind of topics that I plan to have on the exam. But mostly it will be kind of similar to last time. In other words, questions about kind of, there's a math question, there's some kind of coding question, and based on lecture slash homework, that kind of things. Okay. It will also be during the second half, so same format, right? Will be during the second half of the class. you'll be assigned to like, your own room on Zoom, and you just do the exam, scan it, and then send back to me. Or I guess upload it, right? Last time did we do upload? I think so, right? Yeah, upload it on Canvas. Any question on this? Okay, so again, I will confirm with you more about where we cut off exactly by the end of this lecture. But again, I do plan to have these as the materials. Okay, so where were we last time? So let's remind ourselves, right? So last time, basically we started, right, with exotic options. And so, by the way, I think they're cutting grass outside my door, so it can be pretty noisy. Exotic options. And so the point of exotic options, right, to remember is, first of all, by definition, they are path dependent. Okay, so they depend on the whole path of the stock. They depend on the whole path of the stock. So because they're path dependent, so pricing by expectation becomes more difficult. And possibly sometimes not possible. I mean, obviously, kind of, this is, the not possible part. Okay, let me say this. Let me backtrack, right? So pricing by expectations come into flavors. We have Monte Carlo in mind, which is like, the way that we just kind of code it up and try to get numerical answers, or we try to get an explicit formula, right? So Monte Carlo simulation, right, as you hopefully have seen through the homework and through your review session, it becomes less precise, right, and more slow, right? And the reason, of course, is because you have to simulate the whole path to get to the price. And actually, you see, even without the path, when it comes to the Greeks, right? When it comes to the delta, the gamma, that kind of thing, even without the path part, right? Monte Carlo simulation is not precise enough for us to get to the delta and the gamma. The proof of that, right, is that the Black-Scholes PDE is not even satisfied if we use the Monte Carlo plugged in, right, for delta and gamma and theta. So anyway, right, there's some issue with Monte Carlo simulation that is not completely satisfactory. But if you just want to focus on the price, it's okay, right? I mean, it's just slow and not as precise. So you just have to really use a lot of simulations. On the other hand, with explicit formula, with closed form formula, this is where I say it's going to be more difficult. And sometimes not possible. And so we need to qualify this, right? Because every time we say something is not possible, is not it's not. I think it's not possible to prove that something is not possible, if that makes any sense. Because how do we know, right? I mean, how do we know that we have tried all the ways? But anyway, so not possible as in like right now with all the technology we know, as far as the best of our knowledge, we don't know of a way to do so. And so as you will see, right, by the way, so there are three different types of exotic options we want to keep in mind: the barrier, the look back, and the Asian. In terms of flavor, both of these have to do with the max of the path, right? And this has to do with the average of the path, or the integral of path, right? And in terms of explicit formula, it's kind of like weird, but somehow we do have the formula for these two guys, because they have to do with the max of the path. Sorry, guys. But for the integral of the path, unless we just have the, you know, the only the integral. Sorry. Yeah, for the integral of the path, unless we only have the integral, the finding the closed form formula will not be possible. Okay, let's proceed. And so for the third part is about the PD. The PD is basically about the connections of the Greeks. And the Greeks here mostly are the delta, the gamma, and the theta, right? But what you want to keep in mind here is that how is it different to the classical Black-Scholes model? Okay, so actually, I mean, many things, basically the classical Black-Scholes model is where we have everything, right? We have the explicit formula, closed form formula. We have the Black-Scholes PDE, right? We have the Black-Scholes formula. We have the pricing by expectation, etc. When it comes to the exotic options, right, things become more difficult on the probabilistic side, and the PD becomes different. So, and by the way, right, like I mentioned before, the Greeks are super important for, you know, the traders, or actually for anyone who deals with exotic options, or who deals with options in general, to be able to be aware of and compute, right, the Greeks exactly to make their decisions. So therefore, to be able to understand the similarity and the difference of the Greeks in terms of the exotic option compared with the Greeks in the classical option, so with the vanilla option, right, will be very important, you know, for the study. So these are the three main points, right? I mean, 2 and 3 rather, that we want to keep in mind. It's like our guideline as we go along. So and we kind of go back and forth, right, between these types. So last time we looked at the barrier option, right, up and out. For barrier option, up and out, we looked at the PD, right? The PD looks like this, right? It looks like minus RV plus V sub t plus V sub x r times s plus 1/2 V sub xx sigma square s square is equal to 0. So if we just focus on the PD itself, this is exactly like classical, right? Black-Scholes PD, nothing different. On the other hand, though, right, we should not let this deceive us, because first of all, the domain of the PD, right? So the form, right? So the equation is exactly the same as the classical, right? Let me not use the word classical anymore, but let's use the vanilla, right? Vanilla call option, meaning the classical setup. On the other hand, right, this is not, we should not let this deceive us, because however, right, the domain is very different, right? For the vanilla option, the domain is, the stock just have to be non-negative. And t, right, of course, is between 0 and bt. This is natural. But for, let's say, up and out, there is a barrier, right? If you go above it, you get to, you expire, the option expire worthless. So in other words, your stock can never be above this level L, and right, the time, of course, is the same, between 0 and the expiration. However, right, this slight difference, I mean slight, introduces, right, all the difference between these two options, the vanilla call and the up and out, right? Because if you draw the picture and compare them, so this is T, right, and this is stock. The barrier, right, lives in this box, right? So this is up and out. While the vanilla call, it kind of lives in this, I don't know, strip or cylinder, whatever you call it, right? There's no restriction on how far the stock can go up. Okay. All right. So in terms of the PE, right, how does that affect anything? Now, let's be a little bit technical, right? But we will always kind of make the connection back to the Greeks. In terms of the PD, right? And I think you have seen this either in your PD course or in your numerical course, that one of the importance of the PD, or one of the signature of the PD, right, is the boundary condition, right? So in other words, without the boundary conditions, then the PD more or less doesn't work. In other words, you need to give a boundary condition for the PD to kind of start making sense out of it. So boundary, right, basically is the boundary of your domain. And for certain reasons, certain boundaries, we don't have to mention it, but it's there. For example, right, let's just kind of walk us through here. When stock equal to 0, right, this boundary, and by the way, so we think of this is the domain, and V, right, the value of the option, V, the value of the option, as a function, right, on this domain, right? So it's going to be a 3D function. The height, right, the V is the height at this point. So at this boundary, for example, right, what is the value of V here? So this is the vanilla call, right? So at this boundary, what is the value of V? At this point, what is the value? Or at this boundary? You see, this is the boundary of what? This is the boundary of S is equal to 0. So if the stop,
or S is like over 0.
correct. So V equal to 0, right? So that's the boundary condition for this one right here. What about this boundary? What is the condition here?
Of the stopping time? Of like T reaching the stopping time? But is like still greater than 0?
This is vanilla call, so there's no time, right? This is big T, so this is at the expiration. At the expiration, what is the value of the option? Just the payoff.
Right.
Right. So with the vanilla call, these two are given, right? And you solve for all the other values, including this one. This one actually is given by the Black-Scholes formula, right? But basically, from the PD point of view, you are given values on these boundaries, and then you solve it back at every point. Is that okay? Now, when it comes to the up and out call, how does the boundary condition compare? What is the value here at this boundary? What's the value of the option when stop equal to 0? Should still be equal to 0, right? And I hope you understand why. Again, because like once the stock hits 0, it will never, right, go back up. Once the stock hits 0, right, because DST is, let's say, RST dt plus sigma ST dWt. So once ST equals to 0, then DST is also equal to 0. That means after that, the stock will never change anymore, right? Our model is such that once you hit 0, you will always stay 0. I mean, like, technically speaking, you will never hit 0 with our model. But if you start at 0, then you will end at 0, that kind of thing, right? So basically, because once you hit 0, you stay at 0, so your option will never have a chance to be above K, right? To be worth something, so V equal to 0 there. So in other words, that's a quick explanation on why on this boundary, right, everywhere, value of the option is equal to 0. Okay, same as this. So these are the same. And that's from the call property. At this boundary, what's the value of the option? Well, it's a call option, so it's still the same, meaning it's S minus K plus. Okay. So the difference, right? The difference is that right here, you have an extra boundary, right? This is the barrier. There's no barrier for the vanilla call. There's a barrier here. And because you have a boundary, so basically you have an extra boundary here. And at this boundary, what is the value of the call option? Oh, sorry, of the barrier option. V is equal to 0 as well, right? Because at the barrier, you can think of it as at the barrier, you already kind of 0 in terms of value. So you see, with the vanilla option, you start with these two boundaries and you solve it back. With the barrier option, you have these three boundaries and you solve it back in some way. Okay. Now, in terms of the option value, you see how even just looking at the boundary condition, you see something like you can learn about some behavior of the value. For example, right, here the option price starts at 0 at this boundary, and if you increase the stock, the V, right, the higher the stock, the higher the V. That's clear, right? The higher the stock, the higher the V. On the other hand, if this starts at 0, but it ends at 0. So it's like it increased, but it will be forced to decrease at some point, right? It increases and it has to be decreasing at some point. While here, right, the stock, the value of the option can keep growing along with the stock. Okay, so that's one big difference. So in terms of the delta, right, the delta of the vanilla call is always positive, while the vanilla of the call, right, of the berry option, the delta of the berry option, if it's close to the barrier, the delta will start to be negative, right? So I think that's what I forgot. I think Meat pointed out last time, if I recall correctly. Another point, right, is that here there is no discontinuity in terms of the option value. Everything is smooth, right? The option value goes to 0 along this boundary as stock price decreases, right? And this is always 0, so this is 0 right here. It's good. On the other hand, right, you see, if you walk along this boundary, because it's S minus K plus, the value keeps going up. On the other hand, right, is because here you hit the barrier, this is 0. So you have this at this boundary, right? To kind of like make sense out of it, it's just very easy. Suppose, right, on the expiration day, suppose you never expired, right, yet. You did not cross the barrier yet. On the expiration day, suppose that your stock price ends up very close to the barrier, but it's not at the barrier yet. Then you'll make a lot of money, right? Because it's S minus K plus. But if your stock slips a little bit to be above it, then you lose everything. So on the expiration day, you see, like there is a huge discontinuity at this corner right here, right? And that, I guess, makes all the difference in terms of like how the numerical algorithm and everything else needs to be, calculated. In other words, if you want to calculate the delta and the gamma, etc., around this point, I think you will need a high precision, right? High precision calculation, because otherwise, right? I mean, like the action of the option is very crazy at this point. That's the observation. So in other words, right? I mean, like the equation itself is the same, but that's kind of, just the surface, right? Looking carefully, right, on the difference. And so the difference between the berry option and the vanilla option is the domain. And the domain, right, makes a whole big difference. And as we go over, right, the other types of exotic options, we'll observe other kinds of difference. Okay, but again, I want you to kind of like be able to make this kind of comparison for yourself to understand, right? I mean, intuitively the working of these options in terms of the Greeks, because that's practical knowledge. Any question? For example, right? I mean, like the fact that things got crazy here might mean that the theta, right? The change with respect to time, the theta of the berry option is probably quite big, close to the expiration time. On the other hand, the theta of a vanilla option, right, I think gets smaller as time at close to expiration time. That's my guess. But again, you might imagine that on an interview question, right, something like this might come up. I mean, if you somehow, right, apply for a option kind of, trading position or some kind of quant trading position with the team that deals with exotic option, then you can be pretty sure that a question like this comes up, right? Basically, observe how the Greeks of, say a berry option compared to the Greeks of, a vanilla auction, for example. And what I want to bring out is, right, the thinking is not about formulaic thinking, like you need to find the exact formula for the Greeks for this guy and the Greek for this guy. That's not possible, or that's not necessary. Being able to draw this kind of picture, right, and think about it intuitively and explain the intuitive reason why things behave in a certain way will exactly, right, will be what your interviewer will be looking for. All right, so any question on this? So the next thing we talked about last time, right, is then we moved on. So that was chapter 4. So chapter 5, then we move on to pricing by expectation. For look back and barrier options. Okay. And so basically, I mean, another name for pricing by expectation is the closed form formula. Closed form formula for the price. And so the point, right, as you can see, is exactly about number 2 right here. That Monte Carlo simulation, at least the naive one, right, which is the only thing we do in this class anyway, because the point of this class is not to teach you advanced Monte Carlo technique, but Monte Carlo simulation is not good enough. For, right, any advanced, any kind of practical purpose in terms of computing the Greeks, right? And I mean, like, I just named the Greeks as one of the example, but the price itself, right, is problematic because in class, I mean, the moment we see that, right, say the true price is 8.25, as opposed to get 8.31, whatever, 8.34, we say, yeah, that's pretty close, and we're happy. In practice, right, this is a huge difference because, right, the traders, right, earn money by just like a tiny gap of 5 cents because they will sell like 1 million shares of that. So if you have a gap like this of, like, I don't know, 9 cents like this, that's a huge gap, and that that's not acceptable, right? In practice, I guess in practice, like, you must get your approximation to be 8.26 to even be tolerable, right? Even less than that. So in other words, like, even with the price where we say this is acceptable for us in class because we don't, we're not that sophisticated, in practice, this is not even good enough. So in other words, right, precision in pricing and precision in calculation, again, some point that we don't really press in this class, is super necessary, right, out there in practice. Just because I guess, when everything is scaled with like 1 million shares or something like that, it becomes super substantial, even with, like, a tiny difference in terms of the price. Anyway, right, so we want a more precise approach. And by the way, right, there's nothing more precise than closed form formula, because by definition, closed form formula gives you everything, right? So that said, it's not practical to expect closed form formula to be available all the time. And this is why, like, even nowadays, right, with all the technologies around, Black-Scholes formula is still relevant because, it's a quick and, dirty way to kind of come up with a precise price for a certain simple scenario, right? No need for approximation. But if you come up with fancy models, then A, right, I mean, like, you need to do calculation techniques to get to the price, and B, you have to kind of wonder how precise, right, can you get. under those models to the price and other kind of calculations. Okay, so here the point of chapter 5 is to be able to give you the closed form formula, right, for the exotic options in terms of look back and vary. Now, needless to say, right, the warning is this closed form formula will be super complicated and tedious. All right, I mean, you think Black-Scholes is bad, this one is way worse. Okay, but worse in a sense of like, the formula looks really tedious, but it's really beautiful and really good if you are looking for something precise. I mean, if you're a trader and you want a precise approach, you'll be so glad to see this, because otherwise, right, there's no way for you to get to a precise calculation of your Greeks. All right, so that's the motivation. Anyway, so now in terms of the technique, right, the main technique is to be able to figure out the distribution of this object right here called the running max of the Brownian motion. Okay, because like I explained roughly last time, right, that look back and vary options somehow has to do with the max, right? I mean, of the path. So the max of the path, something like this. Suppose you look at the max of the path, right? Suppose you just look at this. Will be by the Black-Scholes formula will be the max of this. Now, because this is a constant and the exponential function is increasing, the max can be transferred inside up to here. Okay. Now, I want to caution you that the max does not then transfer into this. The reason is max of the sum is not sum of the max, especially when the term can be negative. On the other hand, right, this term can be easily dealt with through a change of measure. You'll see that through a change of measure, we will, like the Gussanov, we will be able to call this another Brownian motion W hat. So that's a technical detail. Another, but that's easy because we have covered Gussanov, transformation, the change of measure right before. Anyway, right, so this step is technical, but if you look at the big picture, basically to be able to handle the max of the path in terms of expectation, you need to know how to handle the max of some kind of Brownian motion. Okay, so you need to be able to compute probability of this in some way, and that's exactly the point, the main technique. And so actually I didn't even mention the main technique, right? This is the main question rather. So the main technique then, right? So this is I don't know, this is given, or this is arrived at, or this is achieved, right, by the reflection principle, the concept of reflected Brownian motion and the reflection principle. Okay. So first, so there are two things, right? The concept of reflected Brownian motion and then the reflection principle. The concept of reflected Brownian motion is this, that let's say you have a path, right? I think the nodes we call it M. Let me make sure. Yeah. So we have a barrier, right? And this M actually is like the barrier. That's what we think of in our option, except that here is L for the S, right? Is the barrier for S. Notice that when it comes to Brownian motion, it doesn't have to be L anymore, right? So calling it L doesn't matter. It's immaterial. We just call it M for a generic M. So the point is this, that your Brownian motion starts at 0, okay? It does whatever it does. And let's say at some point it will hit the barrier M. After it hits the barrier M, right, it will do whatever it do again. It does again. But so this is W, okay, in time. But along with W, right, what we'll do is, okay, I say, I'll take the same path up to this moment, and which is, by the way, right, a stopping time. And I will reflect it back across this level, okay? So in other words, so this is my B, okay? B tau, if you will. So B is the same as W up to the first time W hits the barrier. Then after that, right, B is W reflected across this level M. Okay. So mathematically, right, mathematically, B will be W before tau, and then, right, sorry. Okay, so this is a mathematical statement that explains this picture. It says it's the same, right, as W before tau. After tau, right, notice this is the, right, this is the increment of W, right, after time tau. If you start with some point and you add with the increment, then you get where you are, right? But if you subtract the increment, then from here, if you subtract the increment, then basically you do the reflection, right? Basically, if you subtract the increment, then you do the reflection. If you add, right, then you get to W. So if you subtract, right, from the level, then you have exactly the reflection. So this is exactly, this piece, right, is reflection of W over M. Okay. So I mean, W tau is just a fancy way to say M, right? Because W at tau is exactly equal to M. But I mean, like, I guess this gives you the flavor that, you know, it's wherever it is that you start to reflect back, where tau is the first time you hit some level. Anyway, right? So this actually is just a reflected path, if you will. But the point is this, that, and right, for different paths, you have different points of reflection, because suppose W is this path, then you start your reflection right from here, for example. Is that okay? So your tau will be here. So the reflection point will be random because it's a stopping time, random time, just whenever W first hits that level. So the whole point of the concept of the reflected Brownian motion is this following lemma that says the reflected path is a Brownian motion. So in other words, right, when you do this kind of strange thing, it's still a Brownian motion, okay? And that's super interesting, right? And actually, when you first see this, it looks like a weird mathematical result. You know, like, why would someone have enough time to reflect things over like this and you know, like, kind of prove something weird like this? So, right, it all starts to make sense when we look at the reflection principle. So this is right here, but the result is interesting by itself, but it won't be helpful until we look at the reflection principle. Where basically, right, remember, what are we interested in? These are some technical result to get to what we want. And what we want, right, is to get to this guy right here. Okay, to get to this guy right here. So the whole point of the reflective Brownian motion is somehow it allows us to get to that guy like this. So this event, let me write here. Okay. So this is the reflection principle. So last time we showed this, and I will not repeat this proof because I think it's some technical stochastic analysis result that's interesting in itself, but we don't need to emphasize too much. So right, look back into the proof there to see what's the point. But I want to kind of focus, right, start with the reflection principle today. So first of all, let's see the point of the reflection principle first before we start to explain why it's true. So the point is this, right? The point of this reflection principle is this, that basically, now you have m as some number, right? M is some kind of like arbitrary number in some way. K is another arbitrary number. They don't have to be integers, okay? They're just some arbitrary numbers. So together on the left-hand side gives you the joint distribution of M and W. In English, what are they? It gives you the joint distribution of the Brownian motion and its running max, right? M is the max of W itself, right here, right? The max up to time t of W itself. So on the left-hand side, you get the joint distribution. And okay, so you may say that, and by the way, right, the object we're after is this guy only in some way. I mean, but actually we need both. But like, so suppose that you're like, okay, but I only want this. So in probability, right, and I hope you remember this from your probability study, getting the joint actually has more information than getting the marginal. So basically you want the marginal distribution of the max. That's fine. From the joint, if you can get the joint, you just integrate out the joint to get to the marginal. So anyway, right, the point is this gives us more information. So if we're only interested in the running max, suppose that's really the question, then still this will get us there, right? So this is what we want. On the other hand, right, this is of course hard to get because we don't understand what this is. And the point is the right-hand side is just a simple distribution of a normal random variable with mean zero invariance t, right? Because that's exactly the reflective Brownian motion right here. Because B is a Brownian motion, this right here is just a normal random variable with mean zero invariance t. That's it. So we can connect this with a known distribution. In other words, right, if you want, this is something like, right, probability of normal 0t is bigger than or equal to 2m minus k, which you can rewrite as 1 minus n of 2m minus k over square root t. because, right, you do divide by square root of t to normalize it, to make into standard normal, right? And then this is bigger, so you do the complement to get to the CDF. Okay, so anyway, that's the point of this reflection principle. Any questions so far?
I have a question.
Yeah.
So, like, I understand this identity or reflection principle, but why are we doing it? Like, why are we reflecting it across? Like, is that going to lead to the pricing by expectation thing, or like?
So I want to clarify your question, Sherry. You're asking why do we cook up this object right here, or
Yeah,
why
I'm
do
just.
we do this?
No, I'm the first one. Like, why are we reflecting it at that point? I'm just kind of curious
No,
behind.
yes.
Why.
So it exactly serves this purpose somehow. So is this right? And I don't know. I feel like someone super smart some time ago, right, was staring at this object for a while. Okay. And then figure, right? And do you agree? Like, so first of all, right, the way of thinking is this. This is what you're after. Do you agree? This is.
Oh, okay, I see. It's a method to get that.
Exactly.
Okay.
Now this is what you're getting at. But like, no matter how much you think, right, this is very, very hard. Then somehow that guy noticed that if you play around with this, right, you get to this identity, first of all, whatever this object is, whatever this weird object is. And so we haven't explained why this this identity is true. But you see that it's actually very simple, right? But once that person realizes identity is true, then that person realized that, okay, so instead of focusing on this object, I just need to focus on this object. Yes. And then somehow by, again, a stroke of luck or whatever, this guy actually is a prime motion. So it's easy. It's easy to get to this distribution.
I see. Yeah, thank you. That answered my
Right.
question.
Yeah. It is really, in math, right? If you have done some math has at some point, like, some uninspirational transformation. You see your professor or someone else does some weird thing and boom, they get the answer. What's the point? The point is actually behind this kind of, pulling the rabbit out of the hat kind of thing is a transformation to make something difficult into something easy. All right. But of course, difficult and easy has to be relative to the context. Difficult and easy here for us is about the calculation. And so the rabbit out of the hat is this guy right here, right? That Sherry was asking, which is weird. And I agree, right? I mean, in all my life, I would never think of going around and reflecting this guy around for no reason, right? But I guess that's why I'm here, and that's why there's some genius out there. But like, the point is that if you somehow do this weird stuff, then its distribution is still very nice, and right, you get this identity. So that establishes all the link you need for your work, right? That's what I can tell you. Any other question? Okay, so why is this true, right? And exactly, maybe here we also give answer to Sherry's question. So, in math, right, in probability, in set theory, to prove a set is equal to the other, right? One set equals to the other. The traditional way is, I hope you know this, to prove that this implies this and this implies this. Is this okay? Because implication means containing, right? A implies B is the same as A containing B. Is that okay? So I don't know. Let's see if you can stare at it for a little bit and see. And by the way, right here, there is a caveat, and I'll explain. M must be bigger than K. Must be bigger than K. So here, right, you can think of the picture. If you look at the picture in your text, right, And let me pause a little bit in the notes. You'll see that right here, right? Oh, by the way, I use X, I mean, the picture has X here, right? But this is K, this is K, right? So W right here is less than level K, right? And B right here, because it's reflected, you see is bigger than M, 2M minus K, right? 2M minus K, okay? So that's a picture. But let's see. So the point is this, that oh my God, it's doing this again. Maybe I should not stop. Okay, let's see. Okay, good. Yeah. So why is this true? Can anyone see why? I mean, if you can show this, then you understand what the reflection principle is about. So meaning, how do you start from here, right? Use this information to conclude this. And by the way, right, the proof of that somehow has to rely on this definition.
This is just a guess, but would we just like use those like definitions to rewrite BT in terms of like WT?
Yeah,
or is it like
that's exactly the way, but can you be more specific, Don? Like in other words, right? That's the idea.
Okay, let me see if I can write it down.
How can you go from here to here more specifically? In other words, I'm curious on why MT bigger than M and WT less than K leads to BT bigger than 2M minus K. If that makes any sense.
Let me think about this.
Say what?
Let me think about this.
Sure. Maybe 5 seconds. I don't know, but 20 seconds. All right, so maybe let me ask everyone, right, this. What does MT bigger than M mean?
It means that the max WT is greater than M.
Yeah, but more. What does that mean for us in terms of this kind of setup?
MT is greater than that condition where WT minus W lowercase t minus W tau.
Say again, Don. I didn't hear you. Means what?
This is just a guess of like, it's basically telling MT is greater than like the reflection of W over M.
I'm not so sure, because if you want to compare M with B itself, I'm not so sure how those two compare. Actually, it's very simple. Because you're right that M is the max, right? M is the max.
Right.
It's the running max. It's the max up to M. But if the max up to M, the max up to time t is bigger than M, that means that W that means W has been bigger than M at some point, isn't it? Bigger or equal to M.
Yes.
So actually, all it means is that tau is less than T.
Oh.
Or actually, tau is strict less than T, I think, because MT is bigger now.
Yeah.
Do you agree? Now, why is this important? Why it's important is because if tau is less than T, if tau is less than T or T is bigger than tau, then which piece of that definition do we use? If tau is less than T or T bigger than tau?
The first condition? Or it's like 1 minus WT?
Hold on. let me see if I actually, sorry, I wrote this wrong, right? Someone chat. I think I wrote this wrong. I should write the reflected part exactly. I think actually no one correct me, right? This is T bigger than tau. Sorry, right? I mean that was nonsense. If what I wrote before is the same as the above piece. Is that okay? It should be this, right?
Oh, I see. Yes.
Yeah, I mean, I have the right idea in mind. I just wrote the wrong thing. So mid is right, the reflected part, meaning this will be right. So this basically in English means B has already been reflected. Is it okay? So I guess my writing is kind of non-scale. So let me rewrite it in big part. So
Sorry, could you re-explain MT greater than M again? I think I got.
yeah. Do ask Sherry. These things are, it is a little bit straightforward, but yes, it can be confusing. So first of all, you have to always remember what MT is. MT, right, means the max, right? Right. But if the max is bigger than this, then that it must have been bigger at some point, right? Otherwise, how can it be bigger? How can it be bigger? Is this okay? But if that just means that you have crossed. That just means that you have crossed M, right? Because if W is bigger than M for some time before T, that means you have crossed W. So, okay, let me be blunt in English here. That means W has crossed M before T. But what do we mean by tau? Tau is the first time that W crossed M. That means the first time must be less than T. But if the first time that you cross is before T, then by the time T, right, W has been reflected.
I got it. Thank you so much. Sorry.
No, it's fine. Right? I mean, again, like I said, this is quite beautiful in some way, I have to admit. It's beautiful, right? Because you see exactly all these things put together. And that's why, again, right, back to your question, Sherry, that somehow this reflection thing looks weird. But you see, it's exactly this kind of line of thought that leads to it, okay? So if W has already been reflected, then that means it should be this, right? In other words, B tau T would be 2M minus WT. Is that okay? Because I mean, right, this W tau is just M. But if this is 2M minus WT, then the WT less than K would be the same as B tau T is bigger than 2M minus K. Are we okay with this?
Yeah, it makes sense right now.
Mm-hmm. So, but, and again, right, are we done here? That means we proved the reflection principle? Have we proved the reflection principle? Not yet, right? And this is usually the mistake of, like, you know, like someone who's new to probability. when you prove something like this, all you prove is this implies this, but you have not proved the other direction. Okay, because otherwise, right, the probability, if this is strictly less contained in this, then probability of this will be strictly less than this. It's not equal. If it's equality that you want, you need to prove both ways. Okay. So how do we prove backward? That this implies and then WT less than K. How do we prove this? What do you think? So this actually, right, has to do with Dawn's observation. I think Dawn tries to connect the reflected part, right, with M somehow. I think maybe I did not give Dawn the right observation. I think there is some connection here in some way. So first of all, right, you know, the other way, right, seems actually the easier one because these are the two pieces and you just kind of use that to conclude that it's one piece. Here you have to go back, okay? But so here all you have is the information about the reflected motion, and you don't have anything about, right, any knowledge about W and M. So, and I hope you see it, right? The key question here is, has B tau T been reflected or not? Do you agree? Because why is it a key question? Because you know the relation between B tau and T and W, right, are different depending on whether it has been reflected or not. So if we don't know if it has been reflected or not, we do not know which part to use, which part of the definition to use. Is that okay? So here, suppose that all we know is this. Is it possible for us to tell if it has been reflected or not?
No. Though we can always assume that is the case, but even then.
Intuitively, actually, the answer should be yes. Why? Because from here, right, what you expected to be able to do is to conclude that you have been reflected, right? This implies.
Okay, yes. Right.
Does that make sense? I'm not saying that you can see this right away. You may, but the point is that if you just even read from the question, right, you see that, okay, they want you to prove this. In other words, somehow this information must be contained in here already. Yes. So somehow this must have been true. Right. And so how do we conclude that? Let me give you a hint. The hint is based on this relation. And by the way, right, do you see this relation is natural? Maybe this relation is not natural to you, right? Why do we have this restriction? First of all, Why do we have this restriction?
To ensure that MT is at its maximum potential.
No doubt, right? I mean, M and K here are just constants. In other words,
Right.
this is a random variable. This is a random variable, right?
Yeah. Mm-hmm.
I mean, I'm just saying this random variable bigger than some arbitrary value. This random variable less than some arbitrary value, right?
Yeah.
It's
Just to make sure that 2m minus k isn't like less than 0 or anything like that.
But why can't it be less than 0?
Because otherwise BT would be like equal to 0. There would be no path.
No, it's fine right now because it's a Brownian motion. It's a Brownian motion. There's no restriction on the Brownian motion being positive. Or this is not a stock, right? This is not our stock. So there's no such restriction. Yeah.
I'm just making a guess. Is it so that MT is bigger than the Brownian motion because it is basically the max of it?
Yes, you're right. That it exactly is about that. But like not quite, but you're 99% there. Because again, right, M is the max of the Brownian motion, right? So in other words, what's the natural relation between MT and WT?
It's greater than or equal. I'm not sure if the equal. I think it's greater than or equal
No,
to.
it could be equal because it could be, right, the max is exactly WT, just reach back to the max.
Yeah.
But something like this. So in other words, right, these are 2 points potentially that M and W can take value. So if you take M less than K, actually so first of all, does this relation make sense if M less than K? First of all, is it possible for us to talk about this if M less than K?
Sorry, the left side of the equation or the right side?
The left side.
Oh, I don't think so because that wouldn't happen.
So you're right and you're wrong. You're right in the sense that that's the point, right? Is this an empty set or not? But no, I think it's still fine because this, if M less than K, this is not a contradiction, right? Because I'm not saying MT is less than M and WT is bigger than K. Then if M less than K, then that's a problem.
Oh, I see.
Do you see?
Yeah.
Again, this thing somehow, right? The direction also matters, so it messes with your mind. But you're right in anticipating that direction, but you're wrong in the sense that actually this still works. Okay, I'll show you. But basically, and I'll show you why. But the natural, right? The natural relation between M. So I want to caution you that if M is less than K, this still makes sense, but some other problems will happen. Okay, I'll tell you. But the natural relation is M bigger than K. All right, I'll show you. And actually, to be blunt, you need this to make this equality happens. Okay, and then I'll show you. So anyway, right? So if M is bigger than K, right? And as I pointed out to you with a big hint, right? This is needed. If M is bigger than K, then what's our conclusion here to begin with? Well, the only thing that we conclude is this. First of all, right? If M is bigger than K, and so by the way, Don, right, is B tau T bigger than M, not bigger than 0. But anyway, 0 is not the level M. But anyway, right, B tau T bigger than M. But, right, what does that allow us to conclude? Does that allow us to conclude, right, that somehow tau has been bigger than T? Right, in mathematical thinking, it's very helpful to know your desired target. This is exactly,
right, I know that.
This is my desired target. You saw it? Why is that true?
Yeah, I mean, like mathematical speaking, you have to like when you're trying to prove something, you already have to like know what's already assumed, so you can just like prove that other thing.
Right,
I
right,
just
right.
haven't thought about why specifically M should be greater than K in that case. But now I do. Yeah.
So, but do you see that why this concludes here? Why this implies that?
Right.
Why
Yes.
is it? Can you explain? In other
So
words,
if we assume that M is greater than K, then we can assume that BT has been reflected at that point, because, so it's greater than M. Therefore, which also indicates that tau is less than T.
I'm not sure I follow your logic, Don,
I'm trying
because
to make a connection.
K here, right? K here is just a comparison to M. These are two arbitrary numbers. So in other words, right, because M is bigger than K, then 2M minus K, right, is bigger than M. And that's why this is bigger than M, that's all. But I'm not sure if it's obvious yet from what you said, right, that somehow this implies that tau bigger less than T. That means, right, what does tau less than T mean? That means we have crossed, right? W has crossed before time T, time little t. Why is it true? So what are we saying here? We're saying that the reflected path, right, is bigger than M.
Mm-hmm.
Why does that mean that? Because why is it that if the reflected path, right, is bigger than M, then so it's not this picture, right? This picture is not that. It should be somehow. If the reflected path is bigger than M, then that means the prime motion must have crossed. So somewhere here, I guess. So maybe I should erase it, right? Up to here only, something like that. Okay. Why is it? Right? Does everyone see? Does anyone see why this is true?
Are we just plugging in the formula, like going into the second case, and that's like the bounds? Like we know that it's been reflected, so we're using the second case. Like this.
So actually, no, right, Cherry?
Oh.
Meat, I'm not so sure. The reason is, so actually Sherry brings up some point. So either you plug in here, you plug in here, right? So why is it that you know that because B tau T bigger than M, then you must plug in the second part and not the first part?
Isn't it because it would be less than M if it were the top part? Or isn't my logic wrong?
Yeah, actually, I think you got something there, and I'm not sure meat if you meant something like that too. But you know, M and T does not compare, right? I'm not sure. Oh, yeah, I don't know what you meant meat when you say M bigger than T. Okay, T is the time, and I assume there's a typo here. But right, so I think Sherry was kind of. I think Sherry is on the point there. So basically, right, is this. B tau, right, is either WT or not, right? If B tau is WT, then can if B tau is WT, then can WT be bigger than M? You know, like what do I want to say here? If B tau is WT, right, then sorry, how my brain doesn't work. If B tau is WT, then that means the W has not crossed, right? That means that WT, right? WT has not crossed M. W has not crossed M by time T. Do we agree?
Yeah.
But that means that if W has not crossed M by time T, then can that mean can that mean that WT is bigger than M?
No.
No, right? So, but that comes from the fact that we assume that so I think that's what Mead was saying too, right? That comes from our assumption that this equal to WT, right? So if the point is, if you assume this, then this leads to a contradiction. Does that make sense? So if this is true, then this leads to a contradiction. So in other words, right, that means this must be this, or tau is less than t. Is that okay? Basically, because if this is WT, then that means you already you must have already crossed. But if you already crossed, then this cannot be WT in some way. Are we okay? So this implies this because of this reason. But if this is true, right? But so that means that, right? So again, the point is this, that if this will implies that WT has been reflected by the fact that M is less than M is bigger than K. And so that means this piece is taken care of, right? That means MT is bigger than M. And then of course, right, the second piece is easy because this is true, then B tau T bigger than 2M minus K must mean WT is less than K because of this. Any question? Are you okay here? So the point, right, is actually very simple, that the reflected, right, and you see why now, right, that back to Sherry's question, that why the reflection. Basically, you know, if you're chasing the max, you see that the reflection cannot be above M, right? Because for K less than M, for M bigger than K, this is always bigger than M, right? So the reflected path cannot be bigger than M unless you have already been crossed at some point. And if it's bigger than M and you have already crossed, then the other piece of the information, which is W, must be less than K. So in somehow, right, I mean, the reflected path kind of gives us a natural control of whether the max has been crossed or not by virtue of this. Okay, and I think that's the natural use of a reflected path, that it allows us to know whether the path has been crossed or not by selecting this judiciously. In other words, the reflected path being above the level of the reflection only if it has been crossed. Any question? Okay, so I hope, right, I mean, everything makes sense. All the pieces of the puzzle fit into places. So, right, I mean, just for the sake of completeness, what happens if M is less than K? What happens if M is less than K? Do we still have this? You see that, right? If M is less than K, then we have this implication, but not this implication. Because, right, I mean, the way it works from here to here, we did not use any assumption on M and K. You can look, no assumption, right? But the point is, right, going back, again, if M is less than K, then we do not know if this number is bigger or smaller than M, okay? And right, that means that because this number is not, we don't know if it's bigger or smaller than m, it just means that the reflected path is at some level. But if the path is at some level below m, then we do not know if the time we talk about is before or after the reflection. So we cannot say that the level has been crossed. So going backward doesn't work. Is that okay? So that's why this identity relies on this. And this is natural anyway, because of this relation. Okay. So I hope that's clarifies things. Again, I mean, like it's a technical piece, but I strongly encourage you to kind of, if you want to understand this better, try to work it out for yourself. Try to draw your own picture. Try to explain it again for yourself. The reason is this reflection principle is not only for this class alone. If you do some Markov chain, some random walk, you will see the reflection principle again in that class, right? In I think I saw it in the gambler's ruin problem, if I remember correctly, or something. But the reflection principle is a very well-known principle. It's not only for the Brownian motion case, right? This trick of reflecting the path so that you can somehow deal with the max. Okay, is a, well, again, right? I advertise it as like a strange trick, but it becomes classical once people know it. All right, so that's that. Now let's move on from this, right? So we got the reflection principle. So what, right? What do we do with this? Okay, so I guess so the consequence, right? The consequence. So the consequence is, first of all, right? We know that the probability of, let's say, MT bigger than M, WT less than W, right, will be, right, probability of a normal with mean 0 and variance T bigger than 2M minus W. Okay. And so actually then we know, right, that it's going to be something like this. Okay. And so this, of course, right, can be calculated. I mean, I would say exactly. Now, exactly is actually, right, definitely wrong. Professor Wu Jun would say that that's nonsense, right? Because I mean, any of this is an approximation. But by exactly, I mean the approximation can be really precise because we have all the, you know, classical approach, numerical approach to calculate this, right? So exactly mean it can be done to any any degree of precision you want. All right, we know all about this. So we know this, okay? So what else do we know? We will also know the joint density of MT and WT. Okay. And this will be formula (5.1) in notes. Okay. So it's going to be, hold on. The joint density of M and W, right? And there's a T here because, you know, it's T, it depends on T, right? And M and W. Sorry, not formula 5.1. This is before that. equals to 2m minus w divided by t square root of 2 pi t e to the minus 2m minus w square over 2t, and then w less than m bigger than 0. Okay. So actually for like the next, I don't know, half an hour for an hour or so, I'm just gonna keep quoting formulas from the notes. All right. And so I will do something that I don't really like to do, which is copy from the notes, because you can read the notes yourself. The point is I want to copy from the notes, but I will also explain to you, right, the highlight and the connection. All right. Because normally I will show you how to derive from one place to another. But I think that's really tedious calculation. I'd rather show you the point and the use of these formulas. Okay. So I'll just copy the notes to highlight what formula you should pay attention to. But like I won't really go into the technical calculations. So first of all, right, this comes directly from our reflection principle. And then, right, as we mentioned, as long as we have, right, w less than m right here. Okay, as long as we have w less than m. Then, right, this is the natural domain of m and w. So you can differentiate with respect to w and differentiate with respect to m. And you get the joint density of these two random variables. Okay. And because, right, I mean, after you get the joint density, then you can integrate out, if you want, with respect to w to get the density of m if you want. But that will be kind of like a tedious task that you may not want to do. Also notice for the natural domain, right, m is bigger than or equal to 0. Why is this true? Why is m bigger than or equal to 0? Because big M, right, is the max of WT. And because the baryon motion always starts at 0. So the max, right, naturally, including the point 0, so the max would be non-negative, right? So that's why this point M here, the value M that we plug in like this. On the other hand, right, notice there's no restriction on how low W can go, right? W cannot just be higher than M, I mean, in terms of density, because, right, I mean, so the natural domain, right, is MT, WT is less than or equal to MT. That's reflected here. And then, right, the max is bigger than 0. That's reflected here. Okay, so that's the joint density of these two guys. Any questions so far? Okay, so let me mention one more object, okay? And we're gonna take a 5-10 minutes break. I think we're on time today, so there's no need to hurry. So even though, right? So now let's go back to what our goal is. Yeah, our goal is to be able to figure out the distribution of this. And we have achieved it, okay? So when we say our goal is to be able to achieve this, we have got it, right? We have got it. Because right here, right? This right here means we achieved our goal of obtaining the distribution of WT. Oh, sorry, of MT. All right. But, right, unfortunately, at this point, the difficulty doesn't stop yet. All right. So, however, this is still not convenient to use for our purpose. All right. What do we mean by this? So what is our purpose, right? Our purpose is always pricing. All right. Our purpose is always pricing. So in other words, right, we want to obtain the formula, right, for V0, which is expectation under risk neutral of e to minus RT, right? And then you got ST minus K plus, and you have the indicator function that the whole path has not crossed L, like that. That's what we want to obtain. And so you see, right, let's just glance at things, all right? I mean, it's a good practice of calculation just to see what's involved. What's involved here? What's involved here is the max of the Brownian motion, right, somehow. So let me say this, something like MT. This ST definitely involves, sorry, M big T, right? Involves WT, right? Or W tilde T, let's say. So maybe let me say something like this. On the other hand, though, right, you see that even if this involved this and this involved this, which justify the joint distribution, you're not going to want to double integrate this out using a density, right? That's the last thing you want to do, because look at this expression and you want to integrate. So in other words, right, even though the joint density will be helpful to calculate this, it's not the best idea to write down the double integral. I mean, in some way, right, this is similar to knowing, right, the density of W tilde T, right? What is the density of W tilde T? The density of W tilde T, right, is this. Because it's just a, you know, a normal with mean zero invariance big T. And use it to compute the Black-Scholes formula. Which is V0, right, almost like this guy, like this, right? I mean, I guess you guys should have memorized the Black-Scholes formula by now. But if you recall, right, the Black-Scholes formula, of course, is S0 ND plus minus K e to minus RT ND minus. Going from here to here is easily 30 minutes of our life, right, in terms of calculation. Like, and if you ask me to do it right now, it will take me some time, right? And I have done it like at least 10 times in my life. But you see, like going from here to here is not that straightforward. It's not a walk in the park. Of course, right? That's the main link anyway, but carrying it out is not, is still, right? Takes some finesse. So the same thing here. Knowing this joint density and use it to bring this out takes, you know, more in between steps. So in other words, right, there's still more technicalities ahead of us. And the main technical tool, right, the main technical tool for, right, our purpose that involves something like MT, okay? Meaning any kind of option that somehow depends on the running max, like the barrier option or the look back. The main technical tool actually is this, weird object called the H function, right? Alpha, beta, K, and B, right? And you saw it in your homework, which by definition is equal to expectation of e to alpha WS plus beta MS, and then WS bigger than K, MS bigger than B. Okay. And this is in section 5.3.1 in note. Okay. So in other words, right, this object, whatever it is, we have a formula for it, right? So the point is this. We have a formula. But actually, it's not that, right? It's not really exactly that. For special values, as you see, right? And in your homework, you see that already. But this is enough for us. This will be enough for us. To express the option price in terms of age. Okay. So you see, first of all, by formula, I mean a closed form formula. So this is exact in some way, right? It's exact, actually not in some way, this is exact, we have formula. So in this sense, right, the function h serves in a very similar role to the n function here, this n, right, this mysterious n, right, the CDF of the normal. This n actually is more familiar to most people studying, I don't know, probability, because they will have to touch on the CDF. This h looks a little bit strange, but if you look at it, right, what is it? First of all, right, it requires you to have, right, so the S here just anchored a time for you, so there's nothing there. It requires a W to be bigger than K, M bigger than MB, so it's like some kind of CDF, isn't it, right? So this part right here is like CDF. Because by the way, right, what is N of X? N of X is the expectation of the indicator function of, right, W1 bigger than X. Sorry, less than X. Right, so like that. That's N of X. So, right, that's this. So you see, having this right here is just a generalization of something like the N function. On the other hand, though, you throw this in. What is this? I'll say this is like moment-gen function. All right. So the point is, like, this construction or this function right here is not super unmotivated in any way. This is quite a standard object, but also why is this structure very good for us in terms of pricing? Remember, right, we deal with stock price model. And our stock naturally is always exponential of something, right? Exponential of something. So exponential of something, exponential of something. So having this exponential structure right here is actually quite natural and conducive for computing, option price. Okay. And so as you see, everything will be expressed in terms of this H function. I mean, Black-Scholes will still come back, as you see, right? But because by now we take Black-Scholes for granted, so I kind of think of anything involving Black-Scholes as normal, right? And then this one is the new piece that we need to introduce. But that's the point. Okay. So I think it's a good place to take a break now. After the break, we will see how, right, we concretely use this function to obtain the price for the loopback and the vary option. Any question before we take a break? All right, so I think let's take a 10-minute break. So it's 10:25 my time. Let's come back at 10:35. Okay. All right, I'll see you. All right, are we back? So let's continue. Oops. All right. So next, right? Let's go over the items. So now, right? So we mentioned this function h, and we have a formula for this for some special values of the alpha. So the special formulas, right? I'm just going to list them out here. I guess formulae, right? They are, I mean, in section, right? 5.3.2, 5.3.3, 5.3.4. Okay, and then of course your homework of this week. I'll say this: you do not have to worry about the derivation here. Do not worry, right? I don't know how to say this. Like, be aware, right, of like the how the formulas are. In general, but don't worry about how the exact calculation works. Okay, so I'm not trying to say that this is impossible or beyond you guys. Definitely not. I mean, if you have 30 minutes, I'm sure you can figure this out. But like again, right, like sometimes something tedious can kind of sidetrack you into something else, and this is not something spectacularly enlightening or anything like that. So I want you to focus on the main points and see, right, why we do the thing we do. So the things we do. So, right, I mean, don't worry about the calculation. All right, but if you have time, just go back and see if, right, I mean, those calculations, how they're carried out. It is quite straightforward. Okay, so then the next point, okay, of the next point of focus for us will be the pricing. Right, so as the closed form formula for up and out option. Okay. And so, first of all, we need the followings, right? So, like I said, I will go through the main points and I'll just highlight the main points of how the calculation works. First of all, remember that V0 is something like this. Or rather, I think this is, yeah, doesn't matter. E to minus RT, ST minus K plus, and then indicate a function that 0 less than or equal to SU less than or equal to T. So what we'll do is we're gonna change this, okay, into, let me see here. We're gonna change this, sorry, not less than T, less than L. We're gonna change this to two pieces, this, and then this. What am I saying? Sorry, I'm not focusing. The max less than L. Okay, like this. And so here, the second piece will be minus the max. Okay, like this. So 1 and 2. Now, why do we do this? Again, a technical kind of move that somehow this, right, allows us to use the, because, you know, the bigger here, right, is kind of in the same direction as the h function, right? The bigger sign is in the same direction as the h function. So 1, right, is the Black-Scholes formula. And by the way, right, let me reference to, this is formula 5.6 in the notes. Okay, so 1 is given by Black-Scholes formula. 2, right, is what we need to work on. 2 is a new piece. All right, 2 is a new piece. So the max, okay, the max. So we need to deal with this. So the max, right, of 0 less than u less than t of su, as I mentioned, right, will be s0 e to the max of this. The max of this whole thing. All right. And first of all, right, how do we handle this? So we handle it like this. We rewrite so this is r minus 1/2 sigma square times u plus sigma w tilde u. You factor out a sigma. Okay. Why do you factor out a sigma? Because then this will become a Brown motion with drift. All right. This will become a Brown motion with drift. And it can be turned into a W hat, right? Where W hat U will be a Brownian motion under a new measure, the E hat. Okay, so the point being is this, that 2, right, is E tilde, right, this E tilde piece. We can't really calculate this under E tilde because, right, this is not exactly a Brownian motion. So even though we have something like the H function, notice, right, this is E and this is W. So it requires that this must be exactly a Brownian motion, exactly the max of Brownian motion. We do not have it here. We have Brownian motion with drift. Okay, we have Brownian motion with drift because the S has drift. So in order to turn it into a Brownian motion, to use the function H, we need to do one more step where we need to do everything under E hat. So we need to multiply and divide. So to calculate 2, okay? We need to change E tilde into E hat. So in other words, we need to multiply and divide by a change of measure kernel. Okay, to make W hat into a prime motion. So by the way, right, again, this whole thing right here is W hat. All right. Any question about the main idea so far on these steps? Are we okay? All right, so now I will skip, right, the details. So with all of these, all right, you see that we will get to, let me see here. So first of all, right, maybe, you know, let me say formula 5.8 and then 5.9 in book in notes, where 5.8 is under E tilde and 5.9 is under E hat. Maybe let me just point that out to you rather than, you know, copy it again. So here, right? So here, you see this. So in the notes, when I use EQ, that's E tilde. All right, EQ is E tilde, E tilde. All right, and this right here, right, is the second piece, and the X right here is the stock value. Okay, the X right here is the stock value, S0. X is the S0. All right. Don't worry about T minus T. You can think of this T as 0. Okay, little t is 0. So what's going on here? At 5.8, the whole point of this 5.8 is to get rid of the plus, sign on the, you know, option payoff, and change, right, everything involving W tilde into W hat, right, W hat. So you see W hat being this, right, W hat being this. So again, right, if you take little t to be 0, then this is just WT, right, this, and alpha is this guy right here that I mentioned. So this right here, right, is just a step to separate, to take out the plus. So that's why there's an indicator function here to require that W hat must be bigger than this value log so that this is positive. Otherwise it's 0, right? So the formula 5.8 is under E tilde, but rewrite everything in W hat. Then 5.9, right, introduce exactly right here, this change of measure kernel. Okay, 5.9 introduce this change of measure kernel. And so, sorry, let me go back. So 5.9 was already under the E hat, under the new measure. So this is actually the 1 over change of measure kernel. Hold on, E hat is E tilde. Yeah, this is E hat already under the E hat. But so this is the change of measure kernel, but with a negative sign, right? Anyway, the point is that, right, there is a change of measure kernel tagging along as you change it to E hat. That's the point of 5.9. So the final formula for number 2, right, the second item is something like this. And let me draw your attention to, right, the fact that what is it? Aside from all the bells and whistles, right, is E of prime motion, maximum prime motion, some value. And by the way, right, this B is the L, is the barrier. This B is the barrier L, right? I think at that time I used B for the barrier, right? So right here, you see this is the H function. This is the H function, exactly like the H function, with, right, no part on the M, right, on the exponential, but this and this. Any question? Right, so again, just be able to understand, right? Just skip all the steps in between, but understand what 5.8 was doing and 5.9 was doing, and why we do it that way is, and why, right? We kind of do everything to turn it into the structure that can utilize the formula of the H. Are we okay here? All right, so while we're on the roll, right, let me show you too. So finally, right, you see this whole thing right here can be written into the H function, because this is just an H function and this is just an H function. Is that okay? So and then, right, the finally V0 will be the call option, and then the Black-Scholes formula, and then this function right here for the new, so this is the first piece, this is the second piece. Don't worry about this, because here, right, basically here, because this is the formula for V in general at time little t. If you start at time 0, it only means that the stock price at time 0 must be below the boundary, be below the barrier. But of course, you know, if it's above the barriers, you're going to get 0. So essentially, it's going to be the call option for the Black-Scholes, subtract this new piece that we get, that can be obtained by function H. And again, right, what is the point? The point is this is explicit, meaning you can use this. This is precise. You can use this to get to the price of the barrier option precisely, or as close as you want, without any kind of trouble, like Monte Carlo simulation. Question on this? Okay, so let me write down one more message. So the flow of information, right, will be 5.8, 5.9, and then section 5.4.3 for the closed form formula. So let me write down remarks or notation. So EQ, right, is E tilde. B is L. Anything else that I need to tell you? Let T be 0. Okay, so WT is 0. So if you wanted to kind of translate it to our discussion in notes, this is this. This is the notes. This is our lecture. Okay. Questions? So the point, right, is now we can use this closed form formula to calculate the Greeks, right? Calculate the Greeks of the barrier option. Again, right? You know, I think it was Shaoran, right, who showed the class, right, how the calculation was really terrible, right? I mean, when we did the simulation, but for the jump process, right? When we calculate the delta and the gamma, the reason was Monte Carlo simulation is really crude. But now, right, these are precise formula, right? In this section. So when you calculate the Greeks, it should be fine. All right. So in that sense, now you will be asked, right, in your homework or in the review session, I don't know, to study, right, the behavior of the Berry options, right? You should be able to verify the following, right? So remember, this is T, this is stock, right? And this is L, and this is big T, right? The point of interest for us, right, is around this area. So first of all, right, several things, right? Close to here, what happens? Close to here, V should be close to 0. But of course, right, notice the further you go out, the slower it goes to 0, right? Because it's close to expiration. Delta should be negative, right? And over here, right, over this point, I would say large theta and other Greeks. Is that true? Right. So these are, you see, very interesting questions that we ask intuitively. Now we can answer precisely with this formula. Okay. And again, right, I mean, the whole rather boring, I would admit, right, discussion on how to derive the explicit formula, the closed form formula, is exactly for us to be able to study this kind of thing. And right, I hope you appreciate, I mean, as a quant, right, as a future quant, this is exactly the point that you should pay attention to, because your job is to calculate, right, certain things from the model. And if you cannot calculate precisely, right, I mean, I guess the biggest, I guess, downfall of a quant is to think that you can use some tools, right, to do the job while it cannot. So in other words, suppose you know Monte Carlo and you say, oh, I can just do Monte Carlo and everything. Well, that's super naive unless you know advanced Monte Carlo, because right, Monte Carlo cannot do anything sensible close to the right for the Greeks, for example. All right. So this is a technical tools, but again, a very important technical tools for the quant to be able to operate, to analyze this kind of things. Any question? All right. So actually, maybe I just say A, right? B is just to check the Black-Scholes PD, right? Because I mean, you know, how do I know? How do we know that when we do Monte Carlo, the value of the Greeks, right, are not to be trusted? How do we know that? The reason, right, is because exactly, right, from last time that Xiaoran was showing us, when you plug into the PDE, it just doesn't work. It blows up, right? It gets to like 1 million or something. And so, of course, right, I mean, for you guys, you may wonder if I told you the right equation or if I told you, you know, the right thing. From my point of view, because I kind of understand how things work, I know the equation must be correct. Well, what does that mean? Well, that means that our calculation techniques must be wrong, right? So in that sense, like, again, the PDE is a good reality check to see if our calibration makes sense, right? Because if our calibration does not make sense, if errors creep into our Greek calculation, then they won't balance out in the PDE, right? So that's another very practical thing to do. In other words, right, if our Greeks don't satisfy our the PDE, then that means that our calculation has an error. That's it. So this is just another reality check to make sure that, right, our calculation is fine. Okay. Question. All right. So I guess fair warning, another boring calculation coming up, right? So the next one will be for the look back option. Okay. And so what do I want to tell you here? Sorry, one moment. So first of all, right, what kind of look back option are we looking at? So here, the look back option that we're looking at, right? Here we present the floating strike. Look back option. That is V big T is going to be the max. Okay, like this. I don't know about this for sure, but I guess this is a realistic option out there. And if you look at this structure, it seems to make sense. Basically, right, you look at the max of the whole path, but you need to compensate for whatever the value, right, at the end. So basically, whoever buys this option gets the difference, right? If the stock overall has performed well, then they get the max, right, minus the terminal value, for example. But on the other hand, right, if the stock has done something like this, then they're in for, like, you know, terrible. Actually, then they get no payoff, right? Actually, you see, this is almost like a call option in a way. That's why it's called floating strike, because this is always bigger equal to ST, right? So you will get paid, right? But how much you get paid depends on how much the stock has outperformed its terminal value during the whole path. Okay. Now, in terms of mathematics, right, I would say that sometimes the object of interest is just this. Okay. But you see that right, if you know how to do this, then they're equivalent. Let's call this V1, this is V2, right? They're equivalent. Why? Because V2, right, V1 0 is exactly V2 0 plus the stock, right? Because the value of this is S0. So in other words, right, the whole point is just to price this. This is just some addition, right, to kind of turn it into some product that people may realistically buy out there. But mathematically, right, this piece doesn't pose any challenge at all. Is that okay? Question. So for that matter, right, maybe let's just somehow focus on this piece. So let's focus on this expression. So V2T, all right, let's just focus on V2T, which is E tilde of E to minus R, T minus T, the max. Okay. I want to, in the look back option, I don't care, right? I just present it at 0. You know, I'll say the time at 0 is fine. The reason is I don't see any difference between time 0 and time little t. Here, there's some small difference that may be important that I want to bring out. Okay, so that's why I want to do pricing at time little t. rather than pricing at time 0. What's the difference? The difference is how you handle this piece right here. Because this, okay, will be, this is the max of the entire process. It will be the max up to time t. And then, sorry, max up to time t. And then another max. And then take the max of this. Is that okay? So all I'm saying is the max of the entire path is the max up to time little t. Why do I care? Because it's this. And the max from time little t to time big T. Okay. So why do we split like this? The reason is because when you condition on time little t, this part is known. And this part is what we need to take expectation about. So in other words, right, this E tilde here, this E tilde piece applies to this piece only. All right, this is fine. So a peculiar thing, right? So let me say this. A point, okay, of look back option is that V, right, is not just a function of T and ST. Okay. So actually, this is common for most or all exotic options. In other words, if you look at the value of the option, the value of the derivative, and you just know the time and the value of the stock at that time, you would not be able to tell the value of the option. Why? Because it's path dependent. Okay, it's path dependent. For example, right? I mean, actually, this point is simpler than it looks. In other words, for example, if you look at the barrier option, right, and this is T. Suppose at time T, you know that this is ST. Okay, it's below the barrier. Is it enough? Can we tell the option value with this info only? What do you think? So maybe this is a point that I did not kind of emphasize, right, when we discuss barrier option. So here's the stock, here's the time, here's the stock price. Is it enough for us to tell the option value with this info?
No.
What do we need? What else do we need, Sherry?
We need like the stock prices at every time point, like on the path up to that point, I think.
Not quite. With barrier, we can get away with much less. So you're right, but you require too much, right?
Oh,
so
then do we just need to know if it crossed the barrier prior to?
exactly, that's it.
Okay.
But you're right. You're still right. That information somehow involves a path, right? But it's not really the whole path that we need. We need to know whether or not it crossed or not. That's it, right?
Okay.
So that exactly is the encoding. In other words, like the point of all exotic options is that it's not just a function of this, but that doesn't mean that you need the entire path either. Because if you carry the entire path with you, again, that would be too much. All right. So here with the look back option, we only need. So the answer, the answer is right, no. But we need in addition, right, to know whether S has crossed L or not before T. Okay. So when we price, right, when we look at the boundary and we look at the PD, you know, when we price here, of course, the standing assumption is it has not crossed, right? It has not crossed. Because if it has crossed, then the value is 0. There's nothing to talk about, right? So when we do this for the PD discussion, the whole point is, right, we assume implicitly that it has not crossed before we discuss, okay? So right here, with this analysis of the look back option, you see, when we split the max into these two pieces, what does this tell us? This tells us that, so in the case of the look back, so by the way, right, so in terms of the barrier option, the extra information we need, right, so we need T and we need ST, and we need to know whether it has crossed. So we don't need much, but we need that much. In terms of the look back option, V will be a function of T, ST, and an extra process, YT, where Y is obviously the running max of S up to that time. Okay. So in other words, in terms of pricing, if you only know this much for look back option, you cannot tell the price of the look back option. You need this piece as reflected here. Are we okay with this? So, you know, I want to bring up this point, right? This can be missed if we use T equal to 0. Why? At T equal to 0, what's Y0? Y0 is S0. So actually, right, you don't see the dependence if you just look at time T equal to 0. But as time has moved on a little bit, right, then these two values are different. And so, you know, that dependence shows up, right? And we must need this. So that's the point I want to make. I mean, again, right, barrier option also has a flavor. Even if you start at 0, you must start below the barrier. But that can also be missed because you might think that then at any point, if you start below the barrier, you're fine. But that's not true, because if you start anytime after time 0, then you have a history with you, right? You have a history. And if your history somehow has crossed the barrier, then at this point, even though you're below the barrier, your value is 0, right? So there's that. Okay, so that's the first point we want to make. Then the second point, right, will be what? So after we make this point, right, then V2T, right, the value. So again, right, even though the floating strike option is the more realistic option out there, I guess, this is the one, right, of interest, because mathematically, there's nothing to talk about for this aspect T. So V2T, right, will be E tilde of E to minus R T minus T, the max of YT, and ST E to the sigma, right, M hat T minus T, where M hat, right, is the, you know, r minus 1/2 sigma square over u times, over sigma times u plus w tilde u, right, as before. Okay, so like this. So in other words, you see, so in terms of expectation, what we need for the look back option is the joint of what and what. This is the running max of the Brownian motion. What about y? Y itself also involves m hat, because, but it also involves m hat only at t actually, right? Because it's yt. Okay, so wait, hold on. Sorry, I'm talking nonsense. The calculation of this, sorry. In calculating this, right? In calculating this, we treat this as fixed. Sorry, I'm not talking nonsense. It's a fixed because it's known by time t. So the only expectation we need to take is the expectation of this guy right here. Right? The only expectation we need is the expectation of this guy right here. Right? All the guys are fixed. All right. So blah blah blah. The final formula, right, that we have is formula 5.10, where we have v, right, v2t is vtxy, where this is x and this is y. It will be e to minus r t minus t y minus x plus x e to minus r plus alpha square over 2 t minus t times h t minus t alpha sigma minus 30b minus y e to minus r plus alpha square over 2 t minus t times h t minus t alpha 0 minus 30b. All right, that's a mouthful. All right, so where I guess alpha, right, this is only one, alpha is r minus 1/2 sigma square over sigma. So what do I want to say here? Anyway, right, it's really just a ugly formula, if you will, right, in terms of h, y, x, t, alpha, r. Alpha, right, involves the volatility. On the other hand, right, from a calculation point of view, I hope you appreciate that this is a beautiful formula, right? It's a beautiful formula because it allows you to count. Oh, sorry, there's no minus x because let me see here. Give me a moment. There's no x here because the x is exactly the v1. So this is v1. The minus x involves v1. So v2 doesn't have the minus x. Anyway, right? The point is that this, right, is beautiful because it allows us to be able to compute this in a closed form formula precisely. So, right, so with this, right, with this formula, we will be able to calculate, right, the Greeks of the loopback option let's say precisely, okay? And precisely here in quote because, you know, it depends on how precise we can be, but at least more or less precise. Now, let me ask you this. Maybe here. When it comes to the Greeks of a look back option, is there anything new compared to the Greeks of the vanilla option or with the look back option that we see here? Is there something new from this structure that you see that does not show up in the look back? Oh, sorry, in the vanilla option or in the berry option. Do you notice that you have a new Greek? What is this new Greek? V sub y. Right? Because now V is a function of time, stock price, right? Everything else, interest rate, time to maturity, right? Volatility, everything's the same. But there's a new variable, y. What is y? Y is again the running max of the stock up to that point. And so there is a new Greek in town, all right? And that may or may not influence how the relations of the Greeks behave. But at least, right, you see for a look back option trader, right, for exotic option trader who deals with look back option, it is not enough for that person to only care for, you know, theta, delta, gamma in the tradition, you know, of the in the traditional sense of those names. He or she also needs to care of the delta with respect to the running max, because actually, right, there'll be two new deltas. There are two possible deltas. So actually, to be fair, I don't know if this is called deltas, right? But let's just say, in other words, V sub x and V sub y. Okay, because it's either the sensitivity of the look back option with respect to the current stock price, or the sensitivity of the option with respect to the running max, right? Both of these are possible. Okay, what else? Oh, by the way, I mean, I forgot to tell you what B is here. B is 1 over sigma log of y over x. Okay. So there is a new object when we look at the Greeks of the look back option. What that means is the PDE, all right? Again, PDE for us is just the relation between the Greeks of the option price may, right, look different for look back option. In other words, right, we don't necessarily expect that this will happen. Minus RV plus V sub t plus V sub x Rx plus 1/2 V sub xx sigma square x squared to be 0. Does this still hold? Is this true? Because notice, right, this is true for, right, vanilla option and for berry option. Is it true here? We have reason to suspect, right, that this may not hold because you have an extra variable, for example, right? Does it hold or not? Any question? Don, I'm not sure you want to say something. I just saw your microphone kind of is open. Okay, I assume not. All right, then, okay. So that finishes, what is it, section, chapter 5, okay? So now, good, yes and no, right, Don? I mean, so first of all, it's not a question of able to or not. In other words, it's not like, oh, okay, cool, yeah, I just want to make sure that I didn't miss you. The point is this, right, that you're right, but your question is not precise, because it's not like I can add something to the PD, right? Because this relation is somehow very tight, and is gonna be motivated from the martingale structure, right? It's not like this is the Black-Scholes PD, right? It's not like I can come in and I say I don't like this term and I take it out, right? So in the same way, even though we have an extra term here, the right way to say is we expect Y to be present somehow, right, in this structure, but how is not clear yet, and that's the whole study, right? And that's exactly chapter 6. You know what I mean? It's not like you see, okay, there's a Y, so there must be a Y somewhere. Yes, you're right most of the time, but we got to be a little bit more careful than that, right? We want to see, okay, where does it enter? And in fact, right, because I know ahead of time, right, I taught this course many times, it doesn't show up here. Surprisingly, it does not show up here. It shows up in the boundary condition. It's kind of weird, but for agent option, it does show up here. So yeah, we have to be careful. All right. So anyway, right, and exactly what in terms of Don's question, chapter 6 is about a PD for loopback option. Okay. So I want to kind of again highlight the point of chapter 5, right, is it gives you all the tools for calculation of loopback and barrier option, precisely all the Greeks, right? And up to now, you should know how the PDE, how the relation of the Greeks of the barrier option behave, how they're combined. But right, we don't know how the PD for the loopback option combined yet. Most of the time, right, is because of this new variable y, right, the running max of the stock. Okay, so let's review the PD a little bit. Okay, review the PD we got so far. So for vanilla option and for vanilla call and barrier, right? They have the same PD, right? In other words, I mean by PD, by same equation. I don't want to say PD because someone may say I'm talking nonsense because PD cannot just be about equation. This is the same. Right? Different domains. And exactly, right, because of different domains, there are different boundary conditions. So maybe first, right, let us just look at the domain for Asian option. Sorry, for loopback option. So for loopback option, right, we have V as a function of T, right, X and Y, or let's say S, right, and Y. Okay, I hope you don't mind me switching between S and X. S, X, just stock price. So actually, you see now we might have a hard time drawing, right, both. So first of all, I'll do the easy thing. T is always between this and this, right? Because it's between 0 and expiration time. What's the domain for S and Y? any natural boundary on S? Does S have any barrier? Does S have any barrier? No, right? Because it's look back option, unless you want to put a barrier look back option, but we're not, right? We just looking at look back option. So no, right? No barrier. On the other hand, right? Does it mean that S and Y can be anywhere here? So S is positive, Y is positive. This is not true either. Why? Because we have to remember what Y is. What's Y? Y is the max of S. So this is exactly in the same way as M and W, right? M is the max of W, remember? So what's the natural relation between M and W? M is bigger than equal to W. So in the same way here, right? What we have is we have this, and we have S must be naturally less than equal to Y. So the domain is only here. Is this okay? So this is a 3D picture, right? So I only can do, but there's the T, so T doesn't matter. It just runs up to big T. But the domain of Y and S is like this. Are we okay?
Wait, sorry, I have a question.
So,
What you're saying here, I understand the S has to be less than or equal to Y,
yeah.
but like the conditions that you mentioned, they're too loose, right? But they still hold. Like they're still positive. Like both S and Y are still positive, right? Like the max can't be negative and the stock price can't be negative, right?
Sure, because stock being stock, right, cannot be negative. But
Yeah.
the max, because it counts from time 0, right? The max must be bigger than the stock at least. So the max cannot be cannot be negative either, right?
Oh, okay. Yeah, so like the conditions that you like put that question mark next to, those are true, but they're not like
Yeah, they're too loose. Sorry. Yeah, I was putting question mark because I was expecting you to tell me that no, that's not enough. I have to.
Oh, it's not enough, but it is still.
It is true, of course. Yeah.
Okay, just making sure. Thank you.
Okay, so yes, right, like Sherry mentioned, right? So basically these two things together, right? So if you want, you can put this together like this. Okay. Now, what does that mean for us? What that means for us, right, is that there are, so of course there's a boundary at T equal to big T, all right, whatever that is. But that means for us that there is a boundary here. And of course, right, there's a boundary when, S equal to 0, but of course, when S equal to 0, the option price equal to 0. So that's easy, right? This new boundary right here is the one that will be important for us because, for every boundary, what do we need? A boundary condition. So what is the boundary condition? For VTSAYY. Okay, so because, right, this is when X equals to Y, what does it look like? Okay. And of course, right, this is just domain analysis. The equation we haven't set, right? How does the equation look? So two pieces, right, to care for the look back option. What does the equation look like? And what does the boundary condition look like? Here we already addressed what the domain looks like. Is that okay? So I guess, right, to go straight to the answer and, kind of like not having any suspense, the answer will be this. So let me, whoa, too slow. All right. So the conclusion, right? I would write down the conclusion and I will explain it next class. Okay. So this is section 6.6. The PD will be this minus RV plus V sub T plus V sub X Rx plus 1/2 V sub XX sigma square X square equal to 0. So surprisingly, still the same as barrier and vanilla. All right. So this is where I was telling Don that I cheated. I know ahead of time that somehow the y does not enter the equation. But right, I mean, what Don said was perfectly reasonable, that we do expect that to happen. It's just somehow surprising it doesn't. And of course, right, actually the key point then is understand why. Why y does not enter into the equation, okay? But you see that just because it doesn't enter the equation doesn't mean it won't show up overall. It must show up. So first of all, right, it already shows up in the boundary. Like this. So we already need this. This is here. Okay. Second, right here. V sub y at T, y, y is equal to 0. So this is exactly the boundary condition for x equals to y. This one. So what does this say? It says that this delta, whatever that is, right? The sensitivity with respect to the running max actually is 0 at the time that the stock price reach its new max. Okay, very interesting. We need to understand why. Finally, another is when the stock equal to 0, right? This boundary. I think I mentioned in passing that this is 0. Actually, I apologize, right? I'm wrong. I'm wrong. The reason why, right? When stock hits 0, the look back option does not have value equal to 0. Do you see why? Even when stock equal to 0, the look back doesn't have to have 0 value. You see why? Because the payoff of look back option does not depend on the stock. It depends on the whole max, right? So even though the stock hits 0, that doesn't mean the whole path before that was 0, right? Unless the whole path is 0, but it's reflected over here with the running max. As long as y is positive, that means, right, the stock hits 0, but before that, it has been above 0. So you still get some payoff. So therefore, the payoff is e to minus r t minus t times y. Okay, again, we'll explain this. But so the surprising thing is for the boundary condition here, maybe not surprising, right? I'm too careless. When the stock hits 0, the value is still not 0 because the payoff does not depend on the stock itself. The payoff depends on the running max y. Finally, right, the boundary at big T, right, this boundary will be y minus x because it's flowing strike. Remember, so this refers to V1. So that's y and that's x. Okay. All right, so I just want to kind of do this so that I don't leave you hanging. In terms of the exam, I see that I did not, right, cover chapter 6 properly. So let's just go from chapter 1 to chapter 5. Okay. And so the plan of next week is we're gonna discuss chapter 6 and chapter 7 in the first half, hopefully, right? That should give me enough time, and then you do the exam in the second half. All right, I apologize for keeping you a little bit over. I think we're finished for today's lecture. If you have any questions, I'll answer them. If not, then I'll see you next week.
Hello, Professor. I would like to ask some questions. The problem 3 in our homework.
Yes, what's problem 3? I forgot already. Let me take a look.
The brown reflective brown motion.
Yeah. Let's see here.
Should we use the Python?
1 second. Let me see what problem 3 is. Problem 3. We stated the following identity. You asked to verify this. Yeah, you must use Python. Yes.
And how to do it?
So for A, right, what you do is basically, okay, 3, right? Oops. So you have M and you have K, right? You're given M equals to 2, W equals to, oh, yeah, M equals to 2, W equals to 1. So I instead of K. All right. So, so you simulate, right?
Yes.
Path W. Okay. And then from there, you also can compute M. Okay. And so now you do if, right, MT is bigger than M and WT is less than W, then you add count. You add 1 to the count. And then you repeat, right, this for like, I don't know, 1,000,000 times or something, maybe like this, do this. And then your probability, right, will be count divided by 10, right?
Okay. And how about the problem 4? This should also use Python.
Exactly the same way.
Okay. I will try it by myself.
Yeah, it's just pure coding, I think. There's nothing there that is anything too different.
Pseudocoding problems on the next midterm?
Yes, again, pseudo coding, right? I mean, I
Okay,
haven't thought of it yet, but like midterm 1, right? Write down some.
Okay, yeah.
It could be like exactly like what Xiaoran was asking, right? I mean,
Right.
your
About
code,
like
check.
simulating Monte Carlo.
Yeah, something like that.
Okay.
Or, I mean, by the way, right? I mean, the Greeks, the delta approximation
Yeah.
can also be a question. Right? Show me how you can approximate delta and gamma, etc. Right?
Wouldn't we use like the theoretical formulas for that, or just like derived by whatever variable?
So, I haven't formed the exact question yet, but I guess the if I ask a question, maybe I want to check if you know which formula to use. right?
Okay, yeah.
To use, and then what kind of like approximation for delta and gamma, right? Awareness
Okay.
of these things. Does that make sense?
Okay, yeah, I get it.
Yeah.
It just suddenly occurred to me, so thank you.
Sure. Yeah. Again, like, I mean, very similar to the context of the homework, right? I mean, these are questions I asked you, so I'll ask something similar on the exam, hopefully. Yeah. Any other question about anything?
So the exam, it's cumulative, right? So
No, so I won't ask anything about Brian motion, like black shows.
okay.
Hopefully, right?
So
So
it's
focus is on black shows and then on exotic option.
okay.
Sorry, focus on jump process, right? And exotic option. But you're right, Sherry, right? Because I mean, unless I really want to cut out the Brian motion part somehow, right? It still involves somehow about Brian motion, and it still involves, right? I mean, the running max, right? Whatever. But flavor wise, right, I will not hit you on questions like this is the Brian motion, what is, the Ito integral, right? But of course, like it will be Ito formula for jump process. I mean, so it's cumulative by nature, even though I will focus only on the jump process and the exotic option, right? And so for that matter, maybe I'll try to ask questions that just bring out the jump process aspect and the exotic aspect without touching much on Brian motion. But I cannot promise that, right? Because it's just connected in the model. You know what I mean?
Yeah, I see. That makes sense. And also, do we have the same rules? Like we can use like a cheat sheet and then we scan it just like one page, right? Like similar to
I
mid.
mean, since as you mentioned, it's cumulative, I don't mind if you bring 2 side notes. Just
Oh, okay.
add extra materials if you feel like you want to bring along the Brian motion knowledge that you need. I'm fine with that. Yeah.
Okay, I see.
I understand that the material is dense. In fact, I wonder it'll be easier for me to make it open notes, right? There's nothing, it's not open internet, all right? So please don't search questions around. But you can access the notes, because again, what's the point of you copying this tedious formula down and then copy it onto the homework, right? To the exam. So I think I'll make it open notes, all right?
Thank you.
So, yeah. Just there's no point in, right? Okay.
Okay. Thank you so much.
Sure. But I don't think my notes has Black-Scholes formula on it, so you might still want to carry that around.
Yeah. Okay. For sure. Thank you.
Sure. So I'll post an announcement, all right, just to make it official. Any other question? All right, guys. So again, right, thank you for attending. Feel free to leave. I'll stay behind for a little bit if anyone has questions. If not, then right. I mean, feel free
Okay,
to
thank you.
Yeah, thank you, Don. Are you okay, Sharon? Sharon, you okay? All right, I'm going to sign off now, right?